Okay, so then next we have Mikhail Solon from UCLA, and he's going to tell us about scattering amplitudes and conservative binary dynamics under order G to the fourth. I'll give you a warning like 5 + 5 minutes before the end. Please go ahead.
Good. All right, so first, thank you to the organizers. Would have been really nice to see all of you in person, hopefully soon. Hopefully, for example, QCD meets gravity this December might work out, we'll see. Okay, so this talk is about using the tools of quantum field theory. So bringing together both the mathematical and physical aspects of theoretical high-energy physics to tackle significant problems in gravitational wave science. I'll be focusing on our new result, the conservative dynamics at G to the 4 due to potential modes, which appeared earlier this year. But a lot of the technology that comes into here was built upon previous work, and I want to recognize all my collaborators. There's Cliff Chung, Ira Rothstein, Zebern, Radu Royban, Shashan Shen, Mao Zheng, Naba Shah, Julio Parra-Martinez, and Michel Roof. Okay. Of course, the main motivation is that there is this very ambitious experimental program that really began in 2015 with LIGO's detection of gravitational waves, and has continued on with detections of about 50 or so mergers today, soon to be upgraded and soon to be up and running detectors. And hopefully in the future, we'll have 3rd generation detectors, which really means we might have about 1 million mergers detected every year. Okay, so that's a lot of data that could really transform our understanding of basic cosmology, astronomy, and particle physics. And with that, we really also need to bolster up our theoretical understanding of a very basic object in general relativity, which is a two-body dynamics of, for example, black holes. And in this regard, there has been decades of heroic effort from people like Thibault, we just heard from him this morning, people like, and other members of the general relativity community. But it seems like we need new or an invigorated effort that would really bring us to the era of precision gravitational wave science. So that is just to say that it's a hard problem. Now, what could Amplitudes people bring into this game? Well, Amplitudes people have been interested in this, for one, because, well, they have the tools to compute things to very high orders, which is what this is partly about. Second, they know a lot of cool things about gravity. For example, they know how to take the square root of gravity. But in my mind, what I've seen so far is that Amplitudes people are very ripe to tackle this problem because they have the naivete to really attack a hard problem and try to make it easy. Okay, so you're coming from outside and you have no idea how hard the problem actually is. And one way that Amplitudes people have done that so far is to turn the bound state problem into a scattering state problem. So scattering states are easier to analyze than bound states because of relativity. Secondly, scattering states, we can deploy all the tools of theoretical high-energy physics that we've been talking about in this conference, such as on-shell methods, advanced multi-loop integration methods, and effective field theory. And finally, and most importantly, the underlying dynamics between the two of these are actually universal. So there's a lot of information you can get from scattering states that you could then use to really understand mergers that LIGO detects. Okay, and following this set of ideas, this path of research, really I think leads to a set of a program that has the hallmarks of some of the most interesting problems in particle physics. Well, for one, you get to do really adventurous calculations in quantum field theory. Second, you get to explore these new connections that we've heard about between amplitudes and classical physics. And third, the results that you get are of direct relevance to an important experimental program. And that's what I'm going to talk about. Okay, in particular, I'm going to describe to you a pipeline that we use using quantum field theory methods that starts from tree-level gluon amplitudes, uses the double copy to build gravitational amplitudes, uses generalized unitarity to build loop amplitudes, 3-loop amplitudes, advanced multi-loop integration methods and effective field theory to integrate that and get an amplitude out. And that amplitude is then related to classical dynamics, which again, something that's important is that to us is that this is directly useful for LIGO. So what do I mean by that? Well, you can put it in exactly the same space that the functions that LIGO use, in particular this conservative two-body potential, live in. So here is a map of perturbation theory in powers of G and powers of V. And what we've been computing from amplitudes is the two-body potential, which started off with a computation in 2018, which was, I think, Cliff gave a talk on it at Amplitudes 2018. That was the tree level and one loop result. And then in 2019, we computed the three loop result. And I believe Zvi also talked about that at Amplitudes 2019. And then today I'm going to talk about our three loop result at G to the 4. Okay. And as I said, this is the plane on which we can make direct contact with the results that are useful for LIGO. Potential here. This is Einstein, Infeld, Hoffman potential, and so on. So these are the 2PN corrections, 3PN, 4PN, and so on. Today, what is known is this 5PN set of terms. So the traditional way of computing these are along these diagonals, whereas in amplitudes, we could just compute in small powers of G. And what we, oh, sorry, for some reason that didn't show up. What we might need for what papers say we'll need for third generation gravitational wave detectors are so-called 6PN corrections here in light green. And of course, the amplitudes methods, for example, are already slowly understanding some of the terms and that are required for that level of precision. Okay. And as I said, something that's very exciting for us is that this is useful for LIGO. And so our theory friends at LIGO have taken these results and compared them against numerical relativity. So here's a plot of binding energy, for example, as a function of time or orbits to merger. And you can see here the tree level results from QFT, the one loop result from QFT, and the two loop result from QFT all converge towards what is taken as benchmark truth, which is the numerical relativity result. It doesn't quite do as well as EOB, which is a phenomenological model which encodes a lot of information from other sources. But one thing interesting that they point out is that you could also take these results from QFT and encode it into EOB, and it does improve it somewhat. Okay. These are just the results up to two loops, so circa 2019. Recently, there was an updated plot with our three loop results or 4PM results, G to the 4, where now you can see the 4PM result is very close to numerical relativity and actually quite close to EOB. And again, you can take it as input to EOB and see that it does capture some of the physics the same at the same accuracy. Okay. Aside from this, from these that is directly useful for LIGO, there have also been one thing exciting about this line of research is there have been fruitful exchanges between people in the GR community and the high energy physics community. For example, some of the early results here at two loop spurred on new methods of calculating high PN corrections, the so-called tutti frutti method by Bini, Damour, and Garalico, and also the high energy limit, as we just heard from Carlo, led to new understanding of radiative corrections as pioneered by Thibault, and now we understand more about radiative corrections. So there has been a lot of new results, partly because also there are new players in the game. Okay. However, I guess the bottom line and something we would like to work towards is that it is not yet in the pipeline, but it's important to realize that it could be. So these analytic results could actually be useful for making waveforms that are used for detection and inference of properties of mergers. So in particular, analytic results are used here in the early in-spiral phase, whereas numerical relativity is used here in the merger and ring-down phase. So this is something that it would be nice to work towards. Okay. So now let me just go back to the pipeline and tell you some of the details of it. One thing that's very important to the way we compute things is that the classical limit is taken at the earliest stages and at every possible stage you can take it. And that's very important because that's the only hope we can really go to higher orders. There's no way that we can compute amplitudes in full general relativity, including quantum corrections at, for example, 6 or 5 loops, which is what's needed for LIGO. Needless to say, classical limit is the hope towards that, and it makes things very, very simple. So let me say a few things about that. So the process that we are interested in is 2-to-2 scattering, here depicted in the center of mass frame, where you have particle 1 with energy E1 and 3 momentum P coming in, and scattering with particle 2 with energy E2 and 3 momentum minus P. Okay, and then they exchange momentum Q. We are interested in corrections to the potential that describes the dynamics, which go as R Schwarzschild over R, okay, to some power, depending on, so the G powers are buried in R Schwarzschild, and these are the type of corrections we're interested in. In momentum space and writing G in terms of Max Planck, you can write these corrections in this way. Now, the GR amplitude, okay, with Q being one scale and M, typically P, another scale, is just parametrically terms of this form. And the classical limit, in the classical limit is just isolating these pieces, which are exponentiated with exponent C, whereas these quantum terms are suppressed by Q over M. So this is just, as we've heard from Carlo, for example, the soft limit. Nonetheless, it's actually interesting because it's not something that we're used to doing in the usual applications of quantum field theory to particle physics. I mean, obviously we take soft limits there, but when we take soft limits of QED amplitudes, for example, typically it's the quantum terms that dominate because the charge of the objects we're dealing with are actually small compared to the Planck charge. Compare that to the gravitational case where the charge of astrophysical black holes are much, much larger than the Planck mass. Okay, so it is just a soft limit, and we're isolating these kinds of terms in the amplitude, which are enhanced by large charges. Now, one thing that we actually learned is useful is to chop the soft limit further. This doesn't sound like the right thing to do if you're interested in relativistic results, but one thing to realize is that the soft limit still includes quantum pieces, which can complicate and will complicate the analysis at higher orders. In contrast, if we follow the route that is established by the pioneering work of Walter Goldberger and Ira Rothstein, chopping up soft into potential and radiation, then these so-called quantum soft terms are no longer included. One way to think about this is equivalent to computing in the soft limit, but with contribution such that the matter lines are all cut or on shell. Okay, so that's what we're going to do. We're going to further subdivide soft into potential and radiation, and the 4 p.m. result that we're going to talk about today is only from potential. Okay, so for the rest of the pipeline, let me just describe it, although I can probably be brief to this audience on how to construct the integrand, applying the ideas of the soft limit and what is classical versus quantum that I just discussed. We arrive at only 8 classical cuts. The cuts that involve self-energy graphs are not, self-energy diagrams are not included. We also exclude graphs where there are more, where there are not, there's no at least one matter line per loop, okay? And the construction of these is pretty standard and follows the same construction that we used before, namely d-dimensional BCJ double copy brings to construct the gravitational amplitudes. And then using the gravitational tree level amplitudes, we use generalized unitarity to construct the cuts. Once we have the cuts, we can arrange things into Feynman diagrams and then reduce to a set of master integrals using, for example, IBPs using fire. Okay. One thing that's new at 4 p.m., the real new ingredient that allowed for 4 p.m. was really in the integration. So previously, we would take those Feynman diagrams or basis of master integrals and then compute the integrals order and order by V, and then look up the series in the online encyclopedia of integer sequences and then resum. Okay, well, that was fun. Once you see the 4 p.m. result for the amplitude, you realize that that would not have worked. Thankfully, though, there is a very powerful method by Julio, Michel Roof, and Mao for instead of brute force resummation like that, you can just solve these integrals using differential equations. And as Carlos said, we still need the boundary condition. For us, we just evaluate the boundary condition in the potential region using our old non-relativistic integration method. For the experts in the audience, the formula that you might recognize from previous work, which is just that energy integrals are just the sum over matter residues, is still true, except that this weights now SI, these so-called symmetry factors, also depend on the 3D topology. But how this works is, for example, if you take the energy integration of a diagram like this, you weight it by numbers such as 5/24 and 1/8 and cut the matter lines. And so this is how the boundary condition is set. The differential equations themselves are in most cases solved exactly in terms of weight 3 polylogs or elliptic integrals. In a small sector, we had to construct an ansatz, but it was not a big deal. The ansatz was pretty small compared to the number of terms we could check. In fact, everything worked out to something like V to the 500. So that's another nice thing about this setup is that if at some point analytic results are just too hard to come by, you can always determine the boundary condition and then to your heart's content, maybe figure out V to the very high order, which would be still very practical for LIGO applications. Okay, and one adjustment that we had to make in order to merge non-relativistic integration with the differential equation technique was to revisit how we organize the contributions using the effective field theory. So this is an effective field theory for two scalars A and B interacting through a potential. So here's the classical potential. And the amplitudes in this theory are just the so-called bubble amplitudes. Previously, we computed these amplitudes expanding in Y, a pole, which I will describe in the next slide. But crucially, in this work, we had to expand about a new pole, Z. And I will also explain this further, but this is one of the new ingredients at 4 p.m. Okay, so what is this Y pole? Well, you take those, you take that Lagrangian for the EFT, figure out the propagator, and then do these loops. And then the thing is, you want to expand in this variable Y, you find that the structure of these loops have a very simple iterated structure. So it's a classical amplitude iterated twice, classical amplitude iterated 3 times, and so on and so forth, okay? And this was enough for our calculation before. Practically speaking, anytime you have a 1 in Y, you know it'll cancel because then it's an iteration, so you can just drop it, you don't have to compute it. And this is really what determines the classical part of the potential. One cool thing about doing things in terms of this Y basis is that this classical amplitude actually has a simple form in terms of the local 3 momentum squared. So it's the local 3 momentum squared minus the 1 at infinity divided by 2 times the total energy. In other words, you can completely determine these amplitudes to very, very high orders without ever doing loops. You just have to solve for p squared, for example, classically using algebra. Okay. To illustrate that, we could actually do, this is with Nabasha and Cliff Chung, we could actually do all orders in G for some test particle cases. For example, here, this is a test particle in the Schwarzschild background. You could just use this formula and get the amplitude to all orders in G. You can also do it, for example, for a test particle that's tidally distorted, in this case, by electric Weyl squared. And again, you get an all orders in G amplitude. So it's kind of nice because all orders in G amplitudes are very hard to come by. So that was what's nice about the Y basis. But that the Y basis just was not sufficient to merge with the differential equation techniques. So we had to instead use the Z basis. The Z basis is just, instead of expanding in Y, which is 2p dot L plus L squared, you expand in 2p prime dot L, where P prime is the component of the three momentum transfers to the momentum transfer. So in other words, you project the three momentum, you project out the Q dependence of the three momentum, and you want to expand about that direction, okay? The result looks the same. It's still an iteration of the classical amplitude. But what's interesting is that if you look closely at this M prime is exactly just the radial action. So here, the connection between the amplitude and something that is in classical physics, so the radial action is just what determines the classical dynamics in a Hamilton-Jacobi formulation of classical physics. And for example, from it, you could derive Hamilton's equations and so on and so forth. It's exactly just the
10
amplitude.
minutes.
Okay. So here on the left-hand side, you have an amplitude, and which is gauge invariant, and on the right-hand side, you have the radial action, which is also gauge invariant. So another nice thing about this Z basis is that it makes manifest this observation that the amplitudes in the classical limit have a very simple mass dependence. In particular, the tree level one, for example, is just M1 squared, M2 squared. One loop is just M1 cubed, M2 squared plus the swap, and so on and so forth, which means that there is a very clean overlap between results from amplitudes at fixed order in G and self-force results. So for example, 0 SF completely determines the tree level and one loop amplitudes. In other words, Schwarzschild completely determines the tree level and one loop, while 1 SF starts to show up at 2 loop and 3 loop. 2 SF starts to show up at 4 loop and 5 loop. Okay. But the bottom line for us is that it was important to use this Z basis instead of a Y basis in order to merge the techniques of differential equations. So that was the main tool that allowed for us to compute, or one of the new ingredients that allowed us to compute 4PM. Okay, so that's the basic overview of the method. And now let me just show the results. So in these
Mikhail,
results.
sorry, you still have 25 minutes. I mixed up how long your talk was. So
oh,
you have
okay,
anything.
no worries. Yeah. I'm probably going to finish much earlier than that, but that's okay. So in the results I'm going to show you, these are functions of nu, which is just a symmetric mass ratio, capital M, which is the total mass, and sigma, which is the dot product of the 4 momentum of particle 1, particle 2 normalized by their masses. Okay, so, oops, sorry, for some reason. Okay, there. So here is the tree level result. And do you guys see it when I click, or somehow my keynote is frozen? Okay, does it work now?
We can see the screen. I don't know if something else has to show up.
Okay, there. I don't know. My keynote was frozen for some reason. Okay, so here's the tree level result and the one loop result. So you should see M1 equals stuff and M2 equals stuff. And so here, as we said, these are completely determined by Schwarzschild. Factoring out this overall nu squared, you see that the dependence, the functional dependence here is on nu to the 0. So in other words, if you send nu very, very small, you don't lose any information. And that's because these are completely controlled by just a test particle in the Schwarzschild background. A 2 loop, factoring out this overall nu squared here, you see that this function is now linear in nu. If you send nu very, very small, there's a piece that survives here, which is given by Schwarzschild, but then there's a piece that remains and is what is computable using, for example, 1SF corrections. Okay. Now here is our result at 4 PM. So this is G to the 4, factoring out the nu squared again. This is just the overall Q dependence, which corresponds to the right powers of R Schwarzschild over R in position space. And it has we wrote it out in 3 terms. First, there is the piece that is the probe limit piece, which is again controlled by Schwarzschild. So if you send nu to 0, then that's what you get. And then there is the 0 SF correction, which is composed of the tail term and the finite piece. Here are those functions. So they are functions of polylogs of weight 2 and some elliptic integrals. These h's are polynomials in sigma, which I'll show in the next slide. Well, we can look at them here. One thing to note is that, again, the high energy limit here does not connect smoothly to what is expected for the ultra-relativistic scattering of massless states, in particular 0. Here, instead, it is a power divergence. So presumably, Carlo and company can compute the radiative corrections and find that it'll cancel with this divergence. Another interesting thing to note is that there seems to be some structure in the H's. For example, you can see electrophile squared here appearing, and there are other structures here which are not completely clear, but not apparent unless you've been swimming in these results. But there are some interesting structures that could be interesting to understand. There is also no difficulty in transcribing these amplitudes to a Hamiltonian. So again, the amplitude is just the radial action. The radial action, from there you can compute a Hamiltonian. And this is, for example, the Hamiltonian at order g squared. Oops. Again, it's frozen. I don't know why. Sorry. Okay, g squared, g cubed, and then the new result, g fourth, which looks very compact, but again, I've expressed it in terms of the amplitude, which was on 2 slides previous to this. Okay, and again, something that's important to us is that this is directly relevant for LIGO. For example, here plotted against numerical relativity and compared against EOB, which is the standard for producing waveforms. And as you can see, interestingly, it works quite well, despite only being part of the answer in the sense that it only includes the potential contributions. In doing this work, it was really important for us to have checks against the literature. In particular, we were able to check 6PN and 5PN results from this paper by Bini, Damour, and Giralico, and by Blumlein, Mayer, Marquardt, and Schaefer. And then later on, there were additional checks by Blumlein, Mayer, Marquardt, and Schaefer, for example, constructing explicitly the canonical transformation that brings our Hamiltonian to ours, and also the next PN order. And then more recently, there was a paper by Lapa, Calin, Liu, and Porto computing the full PM, redoing the full PM calculation using word line techniques, and they find a match. Okay. Okay, so let me conclude. The big picture is that gravitational wave science has opened up a new direction in theoretical high energy physics. And what's really interesting is that it really has the hallmarks of interesting problems in particle physics, namely that we get to have fun with our QFT methods, explore new theoretical concepts relating classical dynamics and scattering amplitudes, and compute results that are directly relevant for an exciting experimental frontier. And finally, this program is in a nascent stage. I only focused on the 4PM result for scalars. There are now many results for spinning black holes with finite sizes to model, finite size objects such as neutron stars, results for radiation. Previous results that were new 2 years ago have now been redone in very, very slick methods. And so it seems like there's just a lot of momentum building towards hopefully having amplitudes methods produce things that will really be in the pipeline, analysis pipeline of gravitational wave detectors. Okay, thanks.
Thanks a lot, Mikhail. So give him an applause. And are there any questions? I see already that David has raised his hand.
Yes, thank you for this review of what is clearly nascent science. Would you please go back to your 3-loop calculation for, I think, what you called F4F?
3 calculation. Sorry, can you repeat the last thing you said?
Yes, you had an expression for M for F, which I hope contains complete elliptic integrals of the first and second kind. Is that correct?
Yes, that's right.
Can you take us back there? Right.
Right,
because very, very good. This is something which I was told earlier in the conference, and I'm very pleased to see them. So we finally here progress beyond the level of multiple polylogarithms, and we're starting to see the first thing that you might see. Those are complete elliptic integrals of the first and second kind. What sort of mathematical structures might you expect to find at the next order in perturbation theory?
I mean, just extrapolating probably polylogs of weight 3. Beyond that, I'm not sure.
Well, let me make a guess. Modular forms. Maybe in 5 years' time, we'll find out whether that guess has anything behind it.
5 is a long time. Okay, 5 years is a long time.
Okay, Lance, you have a question?
Hey, Mikhail, thanks for a great talk. At some point, you pointed to a series of polynomial terms, maybe on the next slide for the H's, and you said that's electrophile squared. And
yeah, so when we were,
what do you mean by that? Because this is a point-like calculation, isn't it?
That's true. It's interaction of 2 point-like particles. This combination right here, 11 minus 30 sigma squared plus 35 sigma fourth, is electrophile squared. The reason you might see it here is because the tail effect is sensitive to.
Sorry, when you say it's electrophile squared, do you mean it's the leading contribution that you get from the electrophile squared operator at
this combination
tree
is
level?
what you, this combination is what you would get if you scattered, let's say, a particle with a higher dimensional operator, so a finite size with a finite size, where the finite size is given by electrophile squared against, for example, a black hole or a point particle.
With the same prefactors too, or different prefactors?
No, these prefactors are different, but this combination is electrophile squared. I mean, it's not totally surprising because this tail effect is related to quadruple moment squared, and you could couple a quadruple moment to E. So 2 factors of that squared could be I squared E squared.
So can that give some insight into how to recover the finite parts under the 1 over epsilon from the tail divergence?
Right. So yeah. So as I said, this is not a complete result because we've only included potential modes. I mean, the insight is simply to now extend the calculation to include radiation modes. So we have to turn on radiation modes. There's not. So one interesting thing actually is that there's not a lot of ways in QFT to do this. So it seems like the path is the path, and we just have to follow it through. There's not a lot of choices given to you. So it seems like if you want a calculation where you turn on radiation modes, it seems to be a well-defined calculation.
Are there similar divergences in gauge theory EFTs, like Quarkonia potentials? I'm trying to remember.
Yeah, these divergences they have analogs in QED, for example.
Yeah.
Just from splitting the regions, let's say soft contributions into potential and radiation.
But I wonder if anybody ever did bound state, things there. Also in QCD for Quarkonia. Right. Thanks a lot.
Yep.
Okay, we still have plenty of time for questions. So is there anyone else?
Yeah, so for example, Raphael points in the chat that lamp shift has the same kind of pole cancellation.
I have one more comment, if I could make it. Those E squared and K squared terms are the integrands of Stefano Laporta's result for the for loop radiative corrections to the magnetic moment of the electron. You're seeing just the, so the next thing, if you start to integrate such things, which you might expect to do at the next order of perturbation theory, then you're touching the type of things that Stefano heroically evaluated in his 10-year program. And I was very pleased to see that he has recently been contributing in Thibaut Damour's talk to bringing that analytical expertise that comes from looking at massive Feynman diagrams into contexts where, you know, we have this idea that someone's found a 10-point elliptic obstruction, but I believe as soon as you start touching the Bessel functions, which you've shown in the previous talk, and these elliptic integrals, we're moving into the area which has been investigated in massive quantum field theory, and most spectacularly by Stefano and the magnetic moment of the electron.
Maybe a comment that someone might find interesting, but we also did this calculation in n equals 8 supergravity, and there are no elliptic integrals.
Oh, you're
My
muted.
hearing isn't good. You did a different calculation and didn't find them. What was the different calculation?
Instead of GR, n equals 8 supergravity.
Yeah, that's a toy model. We're talking about the real world here.
By the way, something I forgot to remark on is that this tail term here, M4T, which you probably heard from Mao, is of course related to the energy loss. So it connects to Mao, Julio, and Michel, and Enrico's calculation.
Right, I don't see any more questions, so we can all thank Mikhail.
Maybe just a quick follow-up on what you just said,
Right.
Julio. So if the toy model doesn't have the elliptics, but it does have the tail effect, for instance.
Yeah. It also, interestingly, doesn't have the probe contribution because the metric
There's also
black
3
hole.
p.m., right?
Yeah.
Okay.
So it's much simpler, but some of the hard parts of the calculation are still there. So it's a toy model, but basically, if you know how to do that, you learn how to do the real world calculation. Okay, so we can thank Mikhail again and also Carlo. And I guess there's a short break, 20 minutes before this